Hello everyone! In this video we'll talk about the VDA and the VPA signals of the CPU that qualify bus access, and we'll start reworking or read and or write signals to take into account VDA, VPA, ready and bus enable. I hope you enjoy! Okay, so if we look at the datasheet for the microprocessor and we look at the pinout, over here, there is one set of pins that I haven't talked about, and that is VPA and VDA. What is VDA and what is VPA? So those are called valid data address and valid program address. And so there are output signals that indicate when a valid memory address is present on the data bus. So there are some instructions where the CPU will do internal operations and data is going to be output on the address and the data bus, but you shouldn't be reading or writing this data. And this is the purpose of the VDA and the VPA pins, is to indicate when the address bus and the data bus are valid. So if you look at the truth table over here, you can see that when both VDA and VPA are 0, it's an internal operation and the address bus may be invalid. So we shouldn't be reading or we shouldn't be writing to our I/O device or memory when this happens. When VPA is 1, it means that it's a program address. So it's currently loading a byte of code, so either an opcode or an immediate. So then when VDA is 1, it's a valid data address. And so this is when the CPU is reading or writing from memory, or loading or writing data. And finally, when both VDA and VPA are 1, it's an opcode fetch. This is when the CPU is starting to read a given instruction. And so if you're familiar with the 6502, this would be the sync pin of the 6502, be represented by VDA and VPA both equal to 1. So in terms of timing, VDA and VPA have the same timing as the address bus and the read-write pin. So this is something we already talked about. And if you look at the instruction operation table, you can see here the state of VDA and VPA for various clock cycles when executing instructions. And you can find some states where both VDA and VPA are 0. For example, here in the jump subroutine instruction, when using absolute A indexing, you can see that in the fourth cycle, the address bus has the program register and the PC plus 2, and read-write is 1, so it's reading, but it's not actually reading because VDA and VPA are 0, so it's an internal cycle. So if you ignore this, you can get into an issue if your I/O device is sensitive to reads. For example, a buffer from a UART could get read by the CPU inadvertently during an internal cycle, and then this could create a bug in your circuits. So we have to update our read-write pulse generation to take into account VDA and VPA. So this is our schematic where we left off the last time. Let's go into the glue logic and add VDA and VPA as inputs. Now the signals that we are interested in is when either VDA or VPA or both are 1, then this cycle has a valid memory address. So we're going to take VDA and VPA and we're going to OR them, and this is going to give us a valid address signal, and I'm going to call that VA. And then it might be useful to also have a signal for the opcode fetch, which is the sync signal. So we're going to take VDA and VPA and AND them, and I only have 3 input AND gates here, so I'm doing it like this, but it's just an AND gate. And so this is going to give us the sync signal. Sync is not really a good name for this. I would really like to call this opcode, but this is the way it's called in 6502 world, so I think I will keep using that. There we go. So let's add these as outputs. And import them in the top level. And for now, we're not using the signals. There we go. So I want to update the debug module to display these. Instead of VDA and VPA, I think we can display the sync signal directly, and also VA. And finally, I think it would be good to have these available in the monitor so that we can ignore cycles that are not valid addresses and also synchronize the opcode fetch. And this will be useful to build a disassembler in the monitor. So let me add these. So thankfully we have 2 pins still available easily on the Teensy. So one thing I've noticed here in the Teensy monitor board is that I should probably connect those pins. So ground is going to ground, that's easy. And then the analog reference is useful only if we do something with the ADC. And since we're not going to use this, I'm just going to connect it directly to ground. Okay, so let's make the modifications on the breadboard. Okay, so this is our computer where we left off the last time. Let's make the modifications to the debug module, add the VA and sync signals, and also to the monitor. So VDA and VPA are pin 7 and 39 of the CPU. So we have one here and here. We're going to bring them here to the AC11. There we go. And also to the AHC32. So this is our valid address signal, which goes to pin 42 of the Arduino. And this is our sync signal, which goes to pin 2. And we also need to send them back to the debug module here. So this is the sync. And this is VA. Let's update our monitor so we can display those values. So we have to add the new pins. The sync pin is Arduino pin 27, and the VA pin is Arduino pin 26. Those pins are inputs. Let's read them. Now if sync is active, I will print a star. And if it's not a valid address, I will just print dashes. So let's program the Arduino. And I guess I can just read it directly. Let's reset the CPU and bring it to the first instruction. There we go. So that's correct. 18. Now the second cycle is a dummy cycle. Yes, that's correct. Then we have FB, which is also an opcode. And the second cycle is also a dummy. Then we have C2, which is also an opcode. And then it will fetch 30, and that's going to be only program and not an opcode, so we won't see the star on the monitor. Yes, that's correct. Then we have a dummy cycle. Then we go to the next instruction, A2. And then it's reading 7F, 7F. That's correct. Then it goes to CA. Okay, so this looks like it's working. All right, so now that we have talked about VA and sync, we have to talk about the impact that the VA signal is going to have on our read and write pulse. So we actually only want to read and to write when VA is 1, and so we shouldn't generate a read and a write pulse when it is 0. So we need to add it to this circuit. So let me add a new input here. That's going to be VA, and we'll add it to our test data. And now the circuit that we have previously only works when VA is 1, and when VA is 0, we always want read and write to be 1. So let's modify the circuit. And for now, I'm going to do a naive version, and we'll see later how we can optimize it. There we go. Now that we're here, I have some further modifications I want to make to this circuit. And that is, we have to take into account the ready and the bus enable pins. So we have talked in one of the earlier videos about the purpose of those pins. Ready is about stopping the CPU as if the clock was held high, and so it's in a data transfer state. So when ready is low, we want our read and our write signal to be active. The other pin is bus enable, and when we take bus enable low, the CPU has to get off the bus in order for other devices to be able to access it. And so similarly, the read and write pulse needs to be off the bus because the other device might want to generate its own read and write pulses depending on its frequency or what it's trying to do. And so we have to disable those signals when bus enable is taken low. So let's start with bus enable. Let's add it to the test. So when bus enable is high, there is no change. But when bus enable is low, we want read and write to be high impedance. And in digital, we can signify that by putting Z in the test case. There we go. And a naive version of that would be to just add a buffer. Of course, we have to add bus enable as an input. And we're going to have to invert bus enable. There we go. And the final signal that we have to take into account is ready. And when ready is low, we want the circuit to behave just as if the clock was high. So let's add it to the test case. Okay, so when bus enable is low, this is high impedance anyway. When ready is high, it's the same behavior as our normal circuit. But when ready is low, it's just like if the clock is always high. So in this case, when the clock is low, we are writing, we have a valid address, bus enable is enabled and ready is low. We are continuing to be writing. And then for the read, we are reading in the whole clock cycle, so this works. Of course, I need to add ready as an input. There we go. And finally, the last change I want to make is regarding the read signal. At the moment, we are reading during the whole clock cycle. Some devices actually use the first part of the clock cycle to do DMA access. For example, the Apple II uses this scheme. It does video access when the clock is low, and the CPU can access memory when the clock is high. And in the case of our CPU, we are only enabling the read buffer on the second phase of the clock cycle anyway. And so I think it's just good practice to do this as well. So let me change this. When the clock is low, we are reading a valid address, bus enable is enabled, and ready is also enabled. We don't want the read pulse to happen. We only want it to happen when the clock is high. There we go. Okay, so this is all the logic that we want for the read and the write pulse. Of course, this is a very poorly optimized circuit. So let's see what we can do in order to fit this in a lower number of gates and to have it run fast. So remember that for the write cycle, we have a constraint. That is, the write pulse needs to happen at a maximum of 10 nanoseconds after the clock. So the delay from the clock to write is a maximum of 10 nanoseconds. Let's see if we can make it fit. Okay, so it seems that we can replace this with an OR gate. Just have to invert the inputs. Yes. Then we can do 3 input OR gates. There we go. Now remember that 3 input OR gates we can't get in a fast version, so we have to optimize this into an AND or an AND. So we can replace it with a 3 input NAND. And we have to invert all the inputs. So for this, we can just remove this inverter here. We can move this inverter here. And we can replace that with an AND. Yes. Okay, so let's consider the propagation delay from the inverted clock to the read and write pulses here. So assuming this is a 74HC00, it has a propagation delay of 1 to 8.5 nanoseconds. We have it here. Then assuming this is a 74HC10, 3 input NAND, can be 1 to 8. And then for the buffer, we can use the 74AHC367, which is a hex buffer. And the propagation delay through that is going to be 1 to 9 nanoseconds. So in total, there's going to be 3 to 25.5 nanoseconds. So of course that is way too slow. If you look at the timing of the RAM, we have the T data hold here, which is the time we have to hold the data valid after the write pulse goes high. And this is 0 nanoseconds. So we have to ensure that this rising edge here happens before the data starts to change here, which is 10.5 nanoseconds after the falling edge of the clock, which means that we need to be sure that the write pulse finishes before 10.5 nanoseconds after the falling edge of the clock. So 25.5 is way too long. Nevertheless, let's start implementing it in KiCad, and we'll update our timing diagrams and see what we're dealing with afterwards and try to optimize it. So let's go into the glue logic, and we're going to redo this circuit here. So we're going to need 2 new chips, the buffer, and the 3 input NANDs. So let me make a bit of space here. So this needs power and ground. The outputs are going to be the read and write pulse. And I'm going to use the B output of the buffer because there are 2 outputs. And we have the A output available for other purpose. Although I don't think we're going to need them. For now, they're going to be no connects. And the inputs we're going to tie high. Then we need our 2 NAND gates. And we'll have a spare one. So as an input, we need a VA. To invert read-write, I'm going to use one of the spare NAND gates that we have. And we need to grab the inverted bus enable from here. And then we need to NAND ready reg, which is our ready input, with the inverted clock. And there we go. So I was able to use the spare 74AC10 in order to do the NAND with the clock, and this one is even a bit faster, so that's good. So let's go into the timing diagrams and investigate where we are and what we need to change in order to make this work. Okay, so this is the timing diagram of the ROM in a read cycle that we had before. And this is the updated timing diagram. So as you can see, the read signal now takes 3 to 25 nanoseconds to trigger after the falling edge of the clock. And similarly, after the rising edge of the clock, there's the same propagation delay, which means that the output enable of the ROM is only triggered here, which shifted the 70 nanosecond timing all the way up to here, but it didn't change the output here because it's still before the chip enable signal. However, we now have an issue here because the output hold of the ROM is the time the ROM will hold the data after the address, the chip select, or the output enable changes, and that's 0 nanoseconds, which means that the data is only held up until 3 nanoseconds after the falling edge of the clock now. However, the read buffer needs the data 9 nanoseconds after the falling edge of the clock. So this is now an issue. What we can start to do is merge these two lines because now we have enough space to show the information in only one. So let me just do that now. There we go. Now the information is all in one line. So in order to fix that, what we can do is we can shift this rising edge to the right by 10 nanoseconds, just like we did with the latch enable signal in one of the earlier videos. We have this clock phase that is shifted by 10 nanoseconds that we can use. Let me add it to the timing diagram now. Okay, so here I've added the new clock phase. Now, if I go into KiCad and do the same as here, so I AND the inverted clock with the delayed inverted clock, I'm going to be able to fix this problem. Let me just clean this up here. So I'm going to call this the inverse of clock plus. There we go. And now we can take this here and add it to an AND gate here. And the result is it's going to shift this edge without shifting this edge. We can't really shift the second edge here because we're at the limit of what the ROM can do in terms of speed here. So I just want to shift this one. Let me update it now. There we go. And now with the read pulse shifted to the right here, the whole time of the ROM data is satisfied because it stays until 10 nanoseconds, which is the earliest where the address could start to change. And the buffer is reading until 9 nanoseconds, so we are within the margins here. And we're also within the margins at the output. So this should work for the read at least. Let's take a look at the same diagram, but for the RAM. This is the timing diagram of the RAM in a read cycle that we had before. Let me make the modifications to the read signal here. So this is the new clock phase. So this is the updated read signal. Okay, so this is the updated RAM data. Let me merge it into one line. And there we go. Here's all the data into one line. And as you can see, we are good on the reading data before the falling edge of the clock. And we are also good for the 9 nanoseconds to the falling edge of the clock here. So this works as well. Now let's take a look at the timing diagram of the RAM in a write cycle. Let me add the second clock. Here is the added clock pulse. And this is the timing diagram with the new write signal. As you can see, this is now a problem because the write recovery and the data hold timings say that the write pulse has to finish before the data can change or the address can change. However, we are changing the address at 10 nanoseconds. And we are only guaranteed to have the data at 10.5 nanoseconds. So this is not going to work. The solution to fix this, at least with this new 25 nanosecond uncertainty in the write pulse, is going to actually shift this edge to the other side. So we are currently shifting it to the right 10 nanoseconds. But if we shift it to the left, then we're going to be able to meet the timing correctly. And then it's going to work. So in order to generate this new phase of the clock that is shifted to the left, we're going to have to rework how we generate the clock and make use of the spare delay lines here of the DS1035. And I think this video has been long enough. So I will do this in the next video. So stay tuned for that one. Okay, so in this video, we've added the new VA and sync signals to our glue logic. We've added them to the monitor so that we can see when we are doing opcode fetches and we can ignore dummy cycles. And we also started working on a rework of the read and write signal, but we haven't finished that yet. That's going to be the subject of our next video. So in the next video, I will finish the rework of the read and write signal. I will fix the timing. This will probably involve some reworking of the clock in order to introduce multiple phases. So that's going to be pretty exciting, I think. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.